Hi everyone, in this video we look at the mechanism of the E2 reaction. E stands for elimination and 2 stands for bimolecular. This term bimolecular comes from our rate experiments. The rate of this particular reaction depends both on the concentration of our alkyl halide as well as the concentration of the base. This is a second order reaction, and as such these two molecules must be coming together in the rate determining step, hence bimolecular, two molecules. Before we start pushing arrows, let's take a look at the products of these reactions here. Let's look at our first example. We are dealing with a secondary alkyl halide reacting with sodium methoxide. Is methoxide a strong base or a weak base? Methoxide is a strong base. Its conjugate acid is methanol, the solvent we're working in here. Methanol has a pKa of 16. If the pKa of our conjugate acid of our nucleophile is greater than 11, we classify it as a strong base. Strong bases reacting with secondary or tertiary alkyl halides lead to elimination products. In this particular example, we get the more substituted transalkene as the major product with minor amounts of our cis and the less substituted alkene. Other strong bases that will lead to these same products are hydroxide as well as ethoxide. These bases are considered to be small bases. They don't have a lot of steric bulk on the back end. We'll contrast that with tertiary butoxide in a moment. If we switch up our base to potassium tertiary butoxide, we still are using a strong base, but now it's sterically hindered. This large tertiary butyl group on the back end of my oxygen brings a lot of steric bulk with it. And what this does is it pushes the regioselectivity to produce the less substituted alkene as the major product, and we get minor amounts of the more substituted trans and cis isomers. So in terms of regioselectivity, we can selectively produce the less substituted alkene as the major product by using a large sterically hindered base. Tertiary butoxide is the perfect example for this. Now we're ready to start drawing our mechanism. We know where we're going. We know that 2-bromobutane reacting with a small, strong base like methoxide leads to the more substituted transalkene as our major product. Keeping in mind our conditions here, they are strongly basic. Basic conditions will favor the formation of anionic intermediates, if any. Therefore, we would not expect any sort of carbocation on this pathway. Finally, the rate law tells us that this reaction is second order, and being bimolecular, two molecules must come together in that rate determining step. Previously, we studied the SN2 reaction. That is also a bimolecular reaction where the nucleophile attacked the electrophile and displaced that leaving group in one step to give our substitution product, here an ether. We can imagine a very similar one-step reaction happening here, except involving deprotonation of the beta hydrogen. The beta hydrogen is at the carbon next door to our leaving group, which is designated as the alpha carbon. The base can deprotonate, form this pi bond with those CH bonding electrons, and lose our leaving group by cleaving the carbon-bromine bond. This one-step mechanism is consistent with a second-order bimolecular reaction and leads to the product that we isolate in the lab. When we switch our base to tertiary butoxide, we have this large tertiary butyl group that brings a lot of bulk with it. Because of this bulkiness, it's going to be much easier to deprotonate this less substituted beta carbon while forming that pi bond and kicking out our leaving group. This leads to the less substituted alkene. And this deprotonation will be much easier at the primary beta site rather than the secondary beta site because it minimizes steric interaction between our tertiary butyl group and the substituents at the beta carbon. We have just drawn a curved arrow mechanism that is one step that shows the deprotonation, formation of the pi bond, and loss of the leaving group. This agrees with our experimental data and produces the products that we see in the lab. Thanks so much for watching.